2021 conference realignments towards critical competition. My name is Jose Luis, and I'm a lecturer in architectural technology at the Harvard Graduate School of Design, and I'm the conference co-chair, and I'm going to be host of this panel. Before we start, I would like to begin by thanking our sponsors and the ACADIA community for making this event possible. If it would not be, we would all not be here if it wasn't for you. We want to make you aware of a few things before we get started. First, this session is being recorded and will be available to registered conference attendees for viewing after the event, and we will be sharing links to all of you with details of how that will work. In this event, only the presenters are able to participate and broadcast their video and their audio. Webinar attendees are able to watch the session and contribute via the Q&A chat and the Q&A interfaces, as we can see right over here. Conference attendees are also welcome to use the chat interface during the event, but we ask, please, that you all remain respectful in your comments and that you observe ACADIA's code of conduct. If attendees have specific questions for the presenters, please use the Q&A function to ask that question, and we will relay those questions to them. Thank you for your cooperation, and we hope that you enjoy this ACADIA 2021 session. Now, let's begin with the session. This year, we're delighted to honor Caitlin Mueller with the ACADIA 2021 Innovative Research Award of Excellence. This award recognizes the significant contribution of Caitlin to the field of computational design and digital fabrication research. Her rigorous and captivating work, spanning the areas of expertise in structural engineering, digital fabrication, computational design, robotics, and machine learning, continues to push the boundaries of what is possible in architecture and construction. Previous award winners include Sean Alquist, include Wes McGee, Madeleine Gannon, and Jose Sanchez, for example. I'm going to say a few words about Caitlin. Dr. Caitlin Mueller is a researcher and educator who works at the creative interface of architecture, structural engineering, and computation. She's currently an associate professor at the Massachusetts Institute of Technology, just down the road, and in the Building Technology program, where she leads the Digital Structures Research Group. Her work focuses on new computational design and digital fabrication methods for innovative, high-performance buildings and structures that empower a more sustainable and equitable future. Professor Mueller earned her PhD in Building Technology from MIT and a Master of Science in Computation for Design and Optimization from MIT, as well as a Master of Science in Structural Engineering from Stanford University and a Bachelor of Science in Architecture from MIT. She has recently contributed to the organization in several major conferences in architecture and engineering, including in 2017, the Design Modeling Symposium, the 2017 ACADIA Conference at MIT, the 2018 International Association for Light Structure Symposium at MIT, which she chaired, and the 2021 AAG Conference in Paris. She's currently developing a new massive online platform entitled Creative Machine Learning for Design. It's a course, which is planned to launch in the fall of 2021. Today, we will have a presentation by Caitlin, followed by a 20 or 25-minute interview with Maria Japlanina, as time permits. And you've already met Maria. She's been introduced in the previous panel. So I will say that she is currently assistant professor at the John Daniels Faculty of Architecture, Landscape, and Design at the University of Toronto. And she's been a really, really active member of the community of ACADIA, and she's currently at the board of directors. Recently reappointed, I believe. Typically, I would now hand Caitlin the award, which I believe has been previously already mailed to her, but if it hasn't, please tell me and we will make do. And so I would like to raise a round of applause for Caitlin in whichever form you are willing to make that, virtually, physically, with emojis. And I'm going to pass the event over to Caitlin for her presentation, which will be followed by Maria's response and questions. Thank you, everyone.
Thank you so much for the kind introduction and for this incredible honor of this award. I'm so delighted to have the opportunity to share my work with the ACADIA community and to hear from you and share the ideas that I'd like to promote about the interface of architecture and structural engineering empowered through computation. So I've entitled my presentation Computing for Performance and Delight, because I think this is central to my motivation for my work that I do with my research group, Digital Structures, which comprises a pretty diverse group of people across architecture, structural engineering, mechanical engineering, computer science, applied math, and we're all united in our interest in performance-driven design for the built environment. And by that, I mean structures like these. These are some of my favorite built projects from around the world. And what's interesting to me about these is not only that they all use material in structurally innovative and efficient ways, but that they demonstrate the diversity and variety in ways that we can do that. Sometimes when people think about engineering and its role in architecture, you might think that that's constraining and overly burdensome and will lead everyone to the same result. But projects like these, for me, demonstrate that the opposite is true, that actually using performance as a driver in early stage design opens up new possibilities, and it's really an expansive method of expanding our formal palette in architecture. This is also important, of course, because of the impact that the built environment has on climate change. I think we all know that about 40% of greenhouse gas emissions are due to the built environment, both due to the operation of buildings, but also due to the materials that are used to construct them. That's called the embodied energy and carbon emissions. And in this recent study by my colleagues, they found that, for example, the Bird's Nest Olympic Stadium in Beijing uses 14 times the embodied carbon per seat compared to the London Olympic Stadium from 2012. So not 14% more, but 14 times more. That's an enormous performance differential that we would not see in any other discipline. And it's really important because it's really causing climate change today. These are emissions that are associated directly with the use of material. And they use the same material. So it really comes down to design decisions and material quantities that directly relate to structural decisions. So I think we can no longer choose to ignore this key question. We really need performance to play a role in design, but it needs to do so in a way that's creative and open-ended. This is really challenging. As we know, as in a design process, as we advance, we learn more about what we're doing. We have less ability to change what we're doing. Early in the process is where the best decisions can be made, especially about global decisions that relate to form and typology and material. But very typically, a structural engineer who can contribute quite a lot to those decisions is not consulted until the design is really crystallized. It's really hard to involve the structural engineer early, even though everyone always says that's what they want to do. It's really hard to do this for a lot of reasons. I think the primary reason is just that these disciplines are very isolated from each other in many ways, except when they occasionally come together to collaborate. The disciplines are literally about the same thing. They're about buildings. It's about the same, the two sides of the same coin. And yet we are so isolated from each other culturally in terms of even how we use computation, how we think about construction, how we educate our students. Two students could study architecture and structural engineering at the same university, go through the whole curriculum, and never meet until maybe 5 years after graduation in practice. And then by that point, these barriers and these divisions between the disciplines have become so crystallized that it's really hard for us to find productive and integrated ways to collaborate. So I think this is critical to overcome this barrier, both on a sort of personal and cultural level, but also maybe on a technological level, so that we can truly integrate engineering thinking in a synthetic and creative way in the design process. I think that's not at all what we do now, despite a lot of our ambitions to do so. I'd say, if we're thinking about how designs get built or where designs come from in practice, very typically we start with some kind of ideation phase where in the architect's office, we're coming up with different concepts. And then when one is sufficiently mature, it gets selected and sent over to the engineer, and that takes a long time to get an answer. And then the engineer usually says either yes or no. In this case, no, this design's not sufficient. So we have to go back to the architect's office, pick another design, send it all the way back over to the engineer, another analysis. Wonderful, this time it works. Obviously, we can see the limitations of this method. We've done almost no iteration. There's been no feedback. It's this very linear, disjointed process in which the engineer is only a checker of the creative process of the architect. And yet most buildings in practice, maybe 85% of buildings that we see in the world, are designed with processes like this. How can we improve this? One obvious way is to improve the connection between the process of design and the process of analysis or simulation. So if we more closely link these, for example, through technology, through software, we could reduce the time it takes for us to get feedback and therefore investigate a lot more options. But this is still basically trial and error. We could improve this further by systematizing this process and creating a parametric design space, for example. And of course, there are many tools that allow us to do this today, although I'd say, again, this is almost never done for sort of major design and kind of conceptual design phase in practice. Maybe 3% of projects really engage this full process. And yet still, it's still just trial and error, right? We have parameters, we can kind of play with them, we can get different designs, we can analyze them. If this were an engineering problem, if we were in an automotive or aerospace engineering space, the answer to this would be super obvious. We would link the whole process together into an optimization loop and automate the process of design. We would search automatically through a parametric design space to find the result that minimized something that we could simulate. And yet, almost no buildings use this method for design in practice. And I'd argue it's not because of sort of technical limitations on the parts of architects or engineers, but really because while this model is really compelling in certain applications, it's really a poor proxy for the full potential of design in architecture and the built environment. It has a lot of power in that it allows us to incorporate simulation in a directed way, but it's also really brittle and really limited. We only get one solution. It's fully automated. There's no way for us to express authorial intent. It can be very slow, much slower than we think intuitively and creatively. It can be incredibly unnatural for us to have to manually parameterize a design problem. All of us who have worked with parametric design know this struggle to force our design problem into the prison of the parametric design space. And then sometimes you do this whole process and the result is so obvious, or it's worse than something you would have thought of by yourself. And then, of course, a lot of these processes are pretty disconnected from construction and materialization. Maybe another way to express this challenge was done so by Charles and Ray Eames much more concisely in the 70s, where they asked, ought form to derive from the analysis of function? And then, of course, the great risk here is that the analysis is incomplete. I would say still, though, function has value. We don't want to throw out function. We don't want to throw out analysis and simulation. That's how we understand performance. And as I've said, I think that's critical in early stage design. And so we can go back to this parametric design space and think about it maybe more holistically. It's not just about finding the optimal solution in this space, for example, the optimal truss in this design space, but it's about exploring the larger landscape that offers increasingly diverse options the more we relax our obsession with the very best solution according to a quantifiable metric. So in this case, structural material required to support a load, which we might consider to be proportional to embodied carbon, a very important metric. And yet there are other metrics that we care about: how the truss looks, how it relates to its context, what its cultural meaning is. And we can balance some of those things with our human intuition, and some of those things, of course, can be measured. I think for me, ideally, we want to balance both of those and explore those ideas simultaneously. So in a lot of my work, I'm interested in promoting computational methods that achieve that balance through human-computer interaction, for example. So this is a tool that I built during my PhD for the design of long-span trusses that achieve performance through shape and geometry. And the tool uses an interactive evolutionary algorithm to present subsets of high-performing designs that it is searching through the design space for, presenting both their scores and their appearance. And then the designer is able to select within them and use those to evolve new designs. So it's this co-design process where the designer and the computer are expressing various goals, either explicitly or implicitly, to find solutions that are compelling according to a holistic set of goals, maybe goals that aren't even expressible, just based on preference and intent. And this process is similar to optimization in some sense. It can find a range of solutions, though, not just one. The designs here on the left are the original worst performing designs, actually. And as we move to the right, their performance improves. All the way on the right are designs that are also similar to those that have been found through analytical optimization processes, like Robert Mayer's roof in Switzerland or Eiffel's tower. Meanwhile, however, there are a lot of other really compelling designs, I think, that are not the solution to an optimization problem. It would be very hard for me to write an objective function for which this is the solution. And yet this might be my best solution as a designer. My ability, it would give me a choice to express my own kind of preferences in humanity and sort of intent. And these design spaces that balance creativity and performance, one of the priorities is diversity in these spaces. And we see more diversity, for example, in more complex spaces where three-dimensional structural load path is possible, where you have a lot of different ways to transfer load and therefore a lot of ways to use material efficiently. And this becomes even more interesting when we add multiple objectives to the problem. So for example, here we can look at how structural efficiency trades off with operational energy efficiency, and again, achieve catalogs of varying designs instead of single solutions. We can look even further for diverse solutions by moving away from a parametric design space and using something like rule-based design, for example, here to generate the pedestrian or kind of iconic bridges. And what I love about grammars is the ability to generate really, really diverse solutions with a single set of rules. And if I query this set of rules randomly, for example, 50 times, I can get 50 different bridges that are dramatically different from each other. This design space is incredibly expansive. And it contains, again, both kind of familiar solutions, but also things that I never would have found by myself. And we can encode in the rules these structural principles so that everything that comes out is structurally feasible. These grammatical design spaces, I think, are still really underexplored, and there's still so much more that we can do, and where there will be a lot of impact. But they're also really challenging to work with because of their kind of open-ended nature. And so a lot of my work still goes back into this parametric prism that I mentioned. So here, for example, if we parameterize this roof truss with 36 design variables, I actually have too many options. I have 5 billions of trillions of design variations that I can't look at, or I can only look at a tiny percentage. Even if I can simulate all of them, which would take a very, very long time, I still have way too many things to consider. I have no way to really systematically understand this design space. And it seems like I'll have to only resort to optimization or random search. So I'm really interested in that problem of how to kind of apply these design space exploration and sort of human meaningful navigation techniques to large problems. And a lot of what my work in this area recently has made use of advances in machine learning, because these design spaces are very powerful, but almost impossible for us to manually or in a semi-automated way navigate. One of the ways that I do this is with an idea called surrogate modeling. This is a technique that's been around for a very long time. It was developed in the 1990s in aerospace engineering. And the idea is really simple. It's that, the motivation is that if we get really fast feedback from the computer, we're able to maintain a creative flow. If the computer gives us a result or an answer to a question in 200 milliseconds or less, it feels real time, and it feels like we're working directly as creative humans and not as kind of button pushers that are waiting for the computer to answer. And this is based on the kind of creative and cognitive theory. And we can achieve this even for simulations that would normally be too slow with a supervised learning model, with a regression model. And the basic idea here is we have some training data. In my case, it's often synthetically generated from a parametric model. We then build some kind of regression model, a neural network, or some other kind of regression model to fit the data, and then use that to make real-time instantaneous predictions of new designs that we haven't seen before. And these models can not only predict kind of individual metrics of performance, like the embodied carbon of a design, but even full fields of simulation results. So in this case, we are modeling a kind of a structural shell, and we're able to see real-time XYZ displacement results as we change the design, not through a simulation that, at least at the time we did this, would either be very slow or require us to go into a different software tool, but through this predictive model that is quite accurate and also quite pleasant to work with because of how fast it is. The same idea we can apply to other kinds of predictive fields. For example, here's another shell where we might be interested in finding the optimal allocation of material across this surface with something like topology optimization. Another really powerful technique that is sometimes very slow to use in an iterative, explorative way. So I might be curious, as I change the shape of the shell, how does the optimal distribution of material change? I could do a topology optimization that would take a little while, take a few seconds or a few minutes, or I could build a predictive model that gives me this result instantaneously. And impressively, I think, across a really wide variety of inputs. So for all of these, on the left is the exact result of the topology optimization. On the right is the predictive model, empowered again by this surrogate model using a graph convolutional neural network. And the model performs quite well. You can see the errors are about 10% maximum, and it's about 2 orders of magnitude faster than running the actual simulation. And what that means for us in design is that it changes this technique that would be a kind of post-processing or separate check into something that's very portable. You don't need fancy software to run this on your computer. It's very fast. So as we're exploring design in a very abstract way, we're also instantaneously getting this materialization information, and also kind of translatable into more into a variety of materialization strategies. So for example, here we're using the output of the topology optimization to influence the sizing in this kind of waffle slab-like form. So we see surrogate modeling as a way to move techniques that were formerly only possible as validation or final steps into the really early design generation phase. One of the challenges with surrogate modeling, of course, is that it's only as good as the data that it's trained on, and it's very expensive in many cases to generate enough data to get a good surrogate model. So you need to generate data over a weekend to get a surrogate model to use on Monday. And then if you want to change your parametric design space, you have to do the whole thing all over again. This has been, I think, a major reason that we haven't seen surrogate models make more of an impact in real design problems so far. Recently, we've been able to show that we can start to make surrogate models that are recyclable or generalizable. So for example, we've built a surrogate model here to predict the behavior of a trussed bridge-like structure. And with the injection of just a little bit more data, we can apply it to a totally different structure, a tower structure that has totally different loading, boundary conditions, geometry, and it performs quite well. So the graph on the bottom here shows basically that with only 20 additional data points, which can be simulated incredibly quickly, our bridge surrogate model has similar error to a native model that was trained on 500 bridge designs, or sorry, 500 tower designs. So we think this is an important step in getting simulation into creative design processes, just making it very fast and accessible and kind of removing it from the domain of proprietary tools. We're very interested in advancing this, of course, but then once we have this feedback, how do we use it in design exploration? As I said earlier, one of the challenges that I think is important with parametric modeling is that these parameters are kind of a pain. It's really hard to establish what they should be and how they are meaningful in terms of performance at the outset. We don't know this inverse relationship between design decisions and design output or design performance, but we would really like to know that. It would be really useful if we could have tuners or sliders that directly relate to the performance objectives that are important in our design. But again, we can use kind of data science and machine learning to try to establish relationships between these two. So for example, here we're creating synthetic new design variables or new parameters that morph this truss in the direction that best correlates with performance metrics that we care about. And we do this using a very old statistical technique called canonical correlation analysis, which finds linear combinations of our original variables, which are X and Y positions of the nodes of the truss. And it finds these combinations that most correlate with performance. And we can similarly do this with principal component analysis to get kind of sets of design variables. This is kind of a dimensionality reduction technique. So it reduces the dimension of our design space, but also finds meaningful direction for us that corresponds with what we care about. And so we can start to explore the space in a more directed manner, but still have a lot of creativity and freedom to do so. More recent advances in machine learning, such as variational autoencoders, which create a low-dimensional latent space representation of a high-dimensional problem, are also really promising in parametric and computational design. In our work, we've been working with conditional variational autoencoders, where we condition this latent space, which is, again, this compressed or low-dimensional representation of a high-dimensional design space, to always have designs that are high performing and to be continuous in terms of performance. So for example, we have this 36-dimensional design problem that I mentioned before. With a VAE, we can compress it into all the way into 2D, so we can actually look at the design space, which for me is always really exciting. And then we see how performance varies as well, and we see that it's quite smooth. So I can interpolate between really, really different designs that are smooth in terms of both their geometry and their performance, but also I can see a lot of variety here. So I maintain the diversity that is so important for me, but I also get to kind of orient myself to the parts of the design space that are most interesting or most relevant in terms of an efficiency perspective. So all of these are efficient trusses that have been found through this variational autoencoder, which then takes me from this chaos into something that's much easier to understand and to find connections and relationships between designs, while again still preserving diversity. And this can also be connected again with a surrogate model so that this performance can be predicted instantaneously. As was mentioned, we've been teaching this at MIT for a few years. We've had a class called Creative Machine Learning for Design, and we're working to turn this into a massive online open course. It's going to launch soon. I hope it's going to launch this fall, but it may be in early 2022. But we're really excited about it, and it encapsulates a lot of what I showed, but even more as well. And we really hope that some of you are able to participate. We also have a lot of tools that encapsulate some of these methods for Grasshopper in a design tool suite called Design Space Explorer. So I also encourage you to look at this if you're interested, and it's also completely open source. So feel free to use any of this in your own work or reconfigure it however it's useful for you. So finally, we've seen these emerging techniques that expand the palette of architecture, for me at least, and improve performance from a structural perspective. But a lot of times the designs that result are efficient in the computer, but very complex in reality. So for example, every truss has a different node, every member is a different length. Conventional construction would say that that's economically infeasible. Digital fabrication and robotic assembly perhaps make these a lot more attainable. Here's an example. This is a truss that's morphing to become more efficient. And as it does so, each node changes its geometry from its neighbor. Each member becomes a different length. But this robot doesn't care. This robot can just as easily extrude a regular standardized lattice, or a lattice, again, whose geometry is driven by performance, or every node and member are different. But the digital fabrication process is indifferent to that issue. We can also explore more complicated topologies and geometry. So for example, with topology optimization, again, we can achieve these very non-standard and interesting structures for efficient load transfer. And we're working on basically generating the equivalent of slicing algorithms that you would use in FDM printing to allow for flexible robotic assembly of non-standard elements. And we're doing that by connecting with state-of-the-art task and motion planning tools from the robotics community and computer science, and connecting them into design frameworks so that, for example, we can either find the way to materialize a structurally optimized system like this. So here we're seeing the output. This is all automatically planned, so the assembly sequence, all of the robotic instructions that account for collision and kinematics are all handled in this integrated planning framework. But eventually we're hoping for this planning framework to be so fast that this can be an input that goes back into design, so that the automated nature of the robotic assembly not only improves our ability to construct this, but also improves our understanding of constructability itself, which has proven really, really difficult to characterize with conventional construction techniques. Maybe as a kind of almost last example, I wanted to talk about a more practical problem that we've been applying these techniques to as well, which are reinforced concrete construction in the global south, where so much urbanization is happening and so much housing is needed. And yet so much concrete is wasted. As we probably know, most reinforced concrete structures are wasting a lot of the material, especially in the floors, where up to 75% of the material is not needed structurally, but is there because it's easier for us to cast rectangles and squares than it is to cast these structurally articulated parts. But with design space exploration and digital fabrication, we can start to access and achieve these geometries in new ways. And we can incorporate the constraints of the fabrication processes that are appropriate in different contexts into these processes. So here we're optimizing a structural floor system of one-way T-beams that are structurally sculpted. And everything is typical about this in terms of the concrete, the steel, both standard materials. The structural engineering code is meeting today's ACI code. The only thing that's different is the representation of geometry and the ability to explore it in this parametric way. And yet we're constraining our parametric model to only contain designs that are buildable with methods that are accessible in the areas we're working. So here we are working with singly curved laser cut steel parts that are welded together to make formwork. This form can be reused 50 to 100 times. And so the savings that are realized in the concrete are not offset by added complexity in the labor. And so we really think this is achievable and highly impactful, and also, again, expanding the kind of interior space that we can create through the expression of structure. Finally, I also wanted to talk about kind of more radical way to think about material reduction and embodied carbon, which is maybe we really shouldn't be using any virgin material, and we should think about how we can upcycle materials that are already available for us in structural ways, either from existing buildings or from the natural world. Things like tree branches that are normally chipped and that degrade and turn into carbon emissions within a year, we could instead salvage and use in generative design processes to construct structures with high strength, really amazing joints that come from the internal fiber structure of trees. Here, this is a project in which we're optimizing or exploring the design space of this grid shell, not to maximize structural efficiency, but to maximize the use of the inventory of tree branches that we have available. And again, combined with advances in digital fabrication, the complexity of this might become minimized, where the toolpath planning can all be automated and the assembly can all be simplified, where we're working with a kit of parts, but our kit of parts is not standard. Our kit of parts is driven by the natural geometry that we've encountered from our found material. So I think design in the built environment can be responsive to available and upcycled material resources, in addition to just using less of the virgin resources that we're extracting, which also opens up a lot of room for creativity and I think use of computation in new ways. So to conclude, I hope you agree that computing for performance and delight is important. Our climate crisis demands that we understand how our buildings are performing. And recent advances in all of these fields we're excited about, I think, can enable better and more natural links between systematic design space exploration that's driven by simulation and performance, and open-ended human-led design processes that are driven by our creativity, and newly affordable digital fabrication methods that can use automation to achieve new forms in the physical world. Thank you very much.
Wow. Thank you so much for this amazing presentation. Digital applause, please. Well, first of all, I would like to again echo the congratulations on this award. On behalf of myself, on behalf of ACADIA membership, and on behalf of the board of directors, I would like to say thank you so much for your incredible contributions to the field and to this organization. And the award it's just such a pleasure to, have this opportunity and this honor to be awarding you with this award and be hosting this event. I'm also going to echo, and I've lost it. There was a comment in the chat. This is such an elegant way of addressing the navigating complex design problems, design spaces problem. Incredibly inspiring work. So I would like to start this conversation by asking you about this this kind of separation between architecture and engineering that you start your presentation with. And I'm wondering if you could share a bit more on your experience of not only becoming this person who can speak both languages across the fields, but also now in your current role, creating a space where architects and engineers and people with various backgrounds can work together comfortably and kind of speak that same language, because languages are clearly not quite the same across the disciplines.
Yeah, it's a super thorny problem, and I think it's not a new problem. It's a problem that's been around since the Industrial Revolution and the division of professions. And it's also not a global problem. In certain countries and certain cultures, the educational system has addressed this by having much more integrated programs for architects and engineers. So I know, for example, in Japan, in Spain, in Belgium, in Sweden, I'm sure in other countries as well, architects and engineers start their education together. They take studios together, they take mechanics classes together and kind of specialize later in the process. And I think that's a very compelling model. That is not the experience that I had. I had this whiplash model that I think a lot of people have, where I studied one thing and then I wanted to study another thing, and I had this mental and psychological challenge of figuring out how to bring those together. And I think not everyone has to become someone who understands both fields equally. I think that is neither practical nor especially interesting, because both sort of dilute the expertise in both areas. but I think we could all blur a little bit towards the other direction. And I mean, I think from an interpersonal and cultural level, there's some really simple things, right? Like just being respectful and not repeating the jokes you've heard from your professors about how boring engineers are or how dumb architects are. I think it's very helpful to not approach the discipline that way and to approach it in a way where we realize we both have the same goals and we're both really interested in the same things. I get a lot of students that I work with at MIT who have similar interests and backgrounds because, I think there's not a lot of places where they feel that they can engage both sides. And a lot of them tell me the same story that, I always thought I was going to be an architect and then I became an engineer or the other way around. So I think many people are actually much more complex than we give them credit for. And these kind of disciplinary labels or this sort of binary division is really not true on a human level anyway. So I think if we are much more respectful and open to each other and have humility ourselves, we can build these relationships. But it takes time and it takes trust and effort, I would say.
Absolutely. There is a question in the Q&A from Stefana, which touches upon the same. I think you've already answered it, and yet I feel compelled to reread it because of the way it is phrased. I think is very elegant, where this culture, kind of the separation between architects and engineers also happens in this bidirectional culture of engineers not daring to tell an architect how to design and architects being told off for not having the technical knowledge of an engineer, and how that is always a space that is incredibly difficult to navigate.
Yeah,
I don't know.
Agreed. And, this is, as I said, it's very pervasive. I believe I've heard that, for example, when Felix Candelo was still in Spain, he went to visit a construction site of Eduardo Torroja, who was a few years older than him. And Torroja told him, I'm sorry, you're just an architect. You're not technical enough. Please get off the site. You can't work with me. And of course, we know what Candelo then went on to do when he moved to Mexico. So I think this is a very bad, this is a very challenging problem that is pervasive and that we need to actively hold ourselves accountable for and really try not to slip into these lazy stereotypes.
Totally. I do work on multidisciplinary projects. There's often this moment of calibrating the evaluation criteria and calibrating aims and goals of each party. Even, in the academic context, publishing at ACADIA and publishing, for example, are different creatures. So also adjusting at that stage of development, I find becomes part of it, part of that bringing disciplines together. I wanted, moving on from duration, which clearly both of us care a lot about. I wanted to ask a question from Cameron in the Q&A. They're asking, do you see the task of bringing surrogate modeling into the mainstream as a problem of developing enough model templates that one of these pre-existing templates could be slightly?
Yeah, I can see two approaches, and I think probably people are working on both approaches simultaneously. One is to kind of advance what we've done so far with our first demonstration of, starting to develop kind of archetypal surrogate models for different typologies or different kind of types of simulation, for example, that could then be nudged towards specific problem types with small additional injections of data. There's also a really compelling idea called physics-informed learning, where fundamental physical laws are also enforced in the learning process by being added to the loss function in the training process. And so,
great.
for example, equilibrium could be enforced in the training of the model. And so you could enforce that. Also kind of promotes generality, although those models seem very challenging to train in our experience. That I think that's definitely going to be useful. The challenge will be making them general enough and kind of broad enough to extrapolate, which is very hard. I think a parallel approach that we're also seeing, but is also challenging, is to work on wild data rather than synthetic data. So to build surrogate models off of, if you have your own firm, your own built work, historical data. If we can find a data format that we can learn on that's meaningful, and that we can learn meaningful relationships between geometry or design characteristics and performance, that would be very powerful. That's what we see in other areas of machine learning, where we're learning on, 10,000 or 10 million images, for example. I think we have a huge challenge with the size of those data sets in our field. We just don't have that much data. So I think that's compelling, but also will only apply in very certain cases where we do have data sets. And then, of course, we have to be very careful about the quality of those data sets.
I believe Maria might be experiencing some technical glitches. So I'm just gonna jump in as well.
Great.
Caitlin, thank you very much for your talk. I thought it was amazing. If I can bring this a little bit to my own, as a professor of computational design myself, I was actually very moved when you first started talking about how designing structures is basically an iterative process, right? So you make a proposal, you kind of analyze it with some structural performance metrics, and then you start in this iterative cycle where you start improving back and forth based on design intent and performance metrics. And how I think I was jumping on my seat when you were talking about the idea of being able to parameterize a structural design so that you could explore the full family of solutions that you can get, and therefore find heuristics, create synthetic data sets, regression models based on the parameterization of a model. A process that very often, I think you used the word prison, the parametric prison, right? The idea that sometimes encoding design intent is perhaps even less feasible or more tedious than the actual iterative process of trying back and forth, right?
Yeah.
And I think I also saw some of that on later parts of your presentation, where you were discussing how these regression models that you were training, the initial ones were trained on regular, obvious structural metrics like deflection, weight of material, etc., etc. But at some point, you started training models that had more of a design intent. So, like, I forget which two metrics you were using in the examples that you showed. More like lightness or like. So, how do you reconcile that? So in 5 years' time, 10 years' time, if you will, what would be a research line that you would like to work on yourself or have your team work with that explore further the idea of using design intent, using design goals, using this idea of the unquantifiable as a target for these so quantitative heuristic models? What may this look like for you in a really wishful future?
Yeah, well, great question. To clarify, I don't think we have not yet done any real ability. We have not proven that we can capture design intent in any metrics yet, I would say. The way that we have typically dealt with design intent is either through human interaction or input, or through kind of targets that we're trying to get towards. So we see this is what you want, and this is the optimal solution, and can we somehow interpolate between those or construct a design space around those so that we can kind of explore the pressures in both directions and compromise. And I think I didn't show so much of that, but that's a major thing that I'm thinking about a lot, is constructing on the fly design spaces around intent and performance. So if if you know, in that my early slides where I showed the little cartoon with the ideation, if instead of manually making this parametric design space, I could cast a net around all of those and make an make a design space automatically, that would be a really powerful way to capture intent without having to measure it, but by saying, okay, I know there's something about all of these designs that you like, that are sort of going in the direction that you want. Can we somehow infer a design space around that? The challenge of that, of course, is around the design representation. And a lot of work that's very exciting that I see, for example, in computer graphics is oriented around shape or geometry representation. I think we're actually getting quite close to being able to do that. If the only way to represent design intent was shape or geometry, I think we will be very close to getting metrics or at least methods for that. But I still worry that actually design intent is not really just about a precise geometry representation. It's much more nuanced and multifaceted than that, and I always find inexpressible. So I think it's something I will continue to be chasing through a variety of means. But yeah, it's something I'm quite obsessed with as well. I agreed. Which
probably to your point, since it's so difficult to encode, maybe we could also use regression models with enough data to find what is that design intent, or to find commonality between different.
I think that's
which we may not even have names for example.
Yeah, no, exactly. And I think it's also obviously completely subjective is so negative, but I mean, it's completely human, right? So design intent for me even changes day to day, or what I liked last week, I don't like anymore. So there's a lot of reasons that that's really hard.
It is.
I'm going to jump in, assuming that my sound is now back. Excellent, yes. To build on that, I'm wondering if you could speculate on this, the difference between design intent and optimization as a potential reasoning for why, early on in your presentation, you compare architecture to automotive field, and how, certain technologies that are basically there by default in some design fields are not there at all in architecture. Whether there's this fear of optimization and simulation kind of becoming more important than the design intent.
Yeah. Sorry, I don't mean to interrupt you. Go on.
Oh, that was me.
No, great. Oh, sorry. Yeah, absolutely. I think, some of my colleagues in engineering here and in other places, when they say design, they literally mean optimization. Like those two terms are completely interchangeable and have the same semantic meaning, which is so interesting to me because, in architecture, it's obviously that's not the case. But I think the tools of optimization, if we don't try to express them as a literal replacement of the design process, as we might see as the goal of systematic design and engineering, but instead as either a way to create a design space, or as a way to use it, generate one alternative. So I don't necessarily need to know. I don't need to accept the optimal solution, but it could be useful to know what it is so that I know how close or far away I am to it. So I think there are a lot of different ways that we can engage with the mechanics and machinery of optimization without resorting to totally subverting ourselves to it.
Thank you. I'm going to jump to a question from the Q&A from Brian Slocum. This part of the conversation leads to my question: the distinction between design space and solution or possible solution space. Could you speak about that? Because it does seem that your work is about narrowing the possibility spaces to something more manageable for designers.
Yeah, that's definitely an insightful characterization. I want to concentrate the design space into its most meaningful format for us as designers. So I don't want to look at the entire thing. I want to find the parts that I'm especially interested in, or that have the characteristics that I know are important for a performance perspective. So yeah, that definitely is a narrowing in some sense, but it's important that that narrowing, for me, I mean, not everybody agrees that like, you know, that generative or algorithmic design is of value and that the computer should participate in ideation. But personally, I'm very motivated by that. I find it incredibly fun, and I'm constantly finding designs I would never design by hand. And so for me, it's I've accepted that that's really powerful. So I don't want to just I don't want to totally avoid that generative power. And so I see this narrowing down as a kind of generative tool. But I think I'm also not necessarily only interested in optioneering or literally generating instances, but in helping a designer understand the problem. So by exploring the design space, even if you don't literally pick one of the designs that you found, you are able to understand build an intuition and understanding for the relationships between different options that you're considering. This one is heavier because it has this really thin area near where the bending moments are highest that you might not have thought about ahead of time, but that are revealed through the process. So I think that's maybe another, it is sort of about narrowing the space, but it's also about improving the meaning that we can extract from it.
Absolutely. I have to say, for me, that moment in your presentation where you show the parameters, like not just exploring the design space, but also kind of, you know, almost flipping the problem upside down and then trying to figure out what are the parameters that you need to modify. That was for me the wow moment when I was just like, whoa, okay, this is, you know, really, really incredible. Similar to, I was just in a bit of a nostalgic moment from physical spaces. I remember watching that extrusion video for the first time with the choreo software. And I believe that was at Robark some few years ago. And the way the audience felt, I don't think I've seen that very often at conferences. It's like quiet excitement across the whole audience floor, which was just so special and mind-blowing. But I'm going to jump to another question from the Q&A that has to do with machine learning applications and uncanny valley in the field of design. And I'm going to kind of speculate a little bit on the question itself and ask you how much of the kind of present work that we see in machine learning applied to design and architecture, like how much of the precedent space there you're building upon, and whether or not that precedent space is primarily in architecture and design or in graphics and computer science.
Yeah, well, great questions. First of all, I just wanted to acknowledge the choreo video, which is the work of one of my PhD students, Yizhang Huang, who is absolutely fabulous. So please look him up if you're not familiar with his work. The question about machine learning and sort of the art and design world versus the computer science and graphics world. Well, first of all, I think we don't have a lot of data to generate architecture relevant machine learning. We have some floor plans. We have a few data sets of floor plans that a lot of people have worked with. We have images from Instagram and Flickr, which mostly represent exterior views of buildings. And I think people have done really creative things with those, but there's only so much that we can get out of those data sets. And I'm sure we'll still see more because our field is really creative and people are figuring out really amazing things. But I think I almost never engage with design through 2D images. And so I find it very frustrating that that's the data representation that a lot of recent advances in deep learning are focused on, because it's, you know, there's some things that are well represented in 2D bitmap images, but many things that are not. And a lot of the things I'm interested in are much more about 3D geometry. So I think we need different data for us to advance machine learning more meaningfully in an architecture context. And as you've seen, I'm usually synthesizing that data, but I'm really excited about not using that data, of getting that data from natural sources, from real designers, because I think the outcomes will be much more surprising and much more interesting. So the uncanny valley question, I think, is so often because of the nature of these 2D photographs that people are creating. And maybe we will see uncanny valley in 3D generative design. And, you know, of course, there are these examples with furniture and things, but I'm just super excited about it. I just want to see more of that and get access to more data. And I think one thing we can do as a community is contribute data collectively that's open source and that a lot of people can use for different problems. So I hope we move towards that.
And with that, I believe we are on time. I'm going to take those two sentences you just said, Caitlin. We can do better than 2D. That's going to be one. And the other one is, I'm all for natural data. I'm going to say it in 2 Post-it notes here for me. That's going to be my ethos for the next semester. I love it. Thank you very much, Caitlin. It was a pleasure. Maria, it was also a pleasure to have you with us moderating this section. Thank you for that. And I'm going to finish by reminding all the viewers that the next panel, which is going to start in 15 minutes, is going to be the workshop panel where we're going to discuss, we're going to discuss some of the results of the workshop session that happened early in September before the conference. Thank you very much for everyone, and see you back in 15 minutes, if not during the networking session in between. See you in a bit.
Thank you.